Hello. In this video, we will go over the dot product. Okay, in a previous video, we went over the basic definitions for vectors, and they included addition, subtraction, and scalar multiplication. So one of the things that you may have asked yourself was, what about multiplying vectors? Can we multiply vectors? Well, it turns out that we are going to define two different types of multiplications of vectors. The first one that we're going to look at is the dot product. Okay, so to do that, we're going to go through and we'll define A, let A be A1 comma A2, and let B be B1 comma B2. Okay, and we're also going to go through and draw a picture. Okay, and we're going to say that this guy is A and this guy is B. Okay, so we're actually going to start off by talking about the dot product by saying that there are two definitions for the dot product that we need to understand, and we really need to understand both of them. So the first definition is that the length of A times the length of B times cosine theta is defined to be the dot product, A dot B. Okay, and then definition two A dot B is defined to be A1 B1 plus A2 B2. So these two definitions both have a purpose. The first definition is used more when it comes to going through and talking about theory with dot products or going through and proving the dot product properties. The second definition has more to do with going through and calculating the dot product. Okay, so let's spend a minute trying to gain a more thorough understanding of this first definition, where we have this length A, length B, cosine theta stuff. All right, so what's going on here is that this left-hand side, what it is if we went through and took vector A here and we dropped down a perpendicular line, okay, onto B, and then we went through and we calculated what this piece would be, assuming that the angle here is theta. Okay, if you go through and calculate what this piece would be using trigonometry, what you're going to get is that this piece is going to be the length of A times cosine theta. Okay, so that's that piece there. And so if you go through and write this left-hand side, you just kind of rewrite it. You can rewrite it as the length of A cosine theta times the length of B equals A dot B. And then what the dot product is in terms of this picture is it's the product of these two pieces. It's the product of this piece here, which you'd get if you went through and took A and dropped down a perpendicular line and just took kind of this piece here, this part of A, you could think of it as this part of A, and multiplied it by B. And the way that this is interpreted, this is interpreted to be this part of A that's in the same direction as B. That's what we're going through and doing is we're taking A and we're taking the piece of it that points in the same direction as B, and we're taking that piece and then multiplying it by B. So another way of looking at it is that if you took A and you aligned the part of it that is in the same direction as B and then multiplied it by B, then you'd get the dot product. So this is the part of A that aligns with B. And then, of course, it's then multiplied by B itself. All right, so the dot product ends up equaling the part of A that aligns with B times B. And I put quotes here because these are actual lengths, right? So it's not B itself, it's the length of B. So it's the length of the part of A that aligns with B times the length of B is equal to the dot product. All right, so that's going to be one of our definitions, is this kind of funky situation we have here where we have A and B, and you take the part of A that points in the same direction as B, and then you multiply them, and then that's the dot product. All right, so there's our two definitions. Is one of them comes from here, and then this other one is this formula. So what I'm going to do in a minute is I'm going to go through and prove that these two are equal, these two formulas, because it's not obvious at a glance that they are. But first, because of the fact that this formula is mainly for going through and doing calculations, we want to make sure that we can actually do them. So let's do a couple examples really quick with this to go through and show that we know how that would work. So let's say that A equals 1, 3, and B equals -2, 4. Then A dot B is going to equal, so what it says is we're going to follow the formula here. It says to go through and take A1 times B1 and then add A2 times B2. So we're going to take A1 times B1, so that's going to be 1 times -2 plus 3 times 4. So we get -2 plus 12, which equals 10. Okay, so that's how you go through and calculate the dot product using this formula. The dot product also can be extended to 3 dimensions. So this whole picture, I drew it in 2 dimensions, but you could take this and imagine that it's in 3. This formula, if you were to go through and do it in 3 dimensions, you just add an additional component, right? So in 3 dimensions, it would be A1, B1 plus A2, B2 plus A3, B3. And let's just check and make sure that we don't have any problems calculating the dot product in 3 dimensions. So we have let A be 1, -1, 2, and let B be 0, 3, 1. Then A dot B would equal, and you don't have to write all this out if you don't want to. It's just 1 times 0, which is going to be 0. -1 times 3, that's -3. 2 times 1, that's 2. And so you're just going to get -1. Okay, so there's a good place to start. Definition 2 is for calculations. So we've gone through and done a couple of calculations. Definition 1 is for theory. And the main thing that you have to understand is, the stuff that I've written here, which is that if you took took the part of it that points in the same direction as B, which would be this stuff here. And again, where does this come from? I didn't go through and write that up, but you can determine that using trigonometry. Okay, so if you go through and play around with trigonometry with this triangle here, you'll get that this side of the triangle is the length of A cosine theta. And then the dot product is this piece multiplied by this piece, by B multiplied by the part of A that points in the same direction as B. Okay, so let's move on. So next we want to go through and prove that these two definitions are equal, right? Because it's not obvious. So to do that, we're going to start off with stating the law of cosines, because that's what we need to do the proof. So what does the law of cosine say? It says that if we have a triangle where this side is, where that angle is theta, and this is A, and this is B, and this is C, then C squared equals A squared plus B squared minus AB cosine theta. Okay, so in order to go through and use the law of cosines, we want to apply it to our situation that we had on the previous slide. Okay, so let's say that this is vector A. This is vector B. And then we're going to need to have this additional side here. And if you recall our vector definitions, if we have vector A and vector B that have the same initial point, then we can get a vector that points between their ends by subtracting the vectors. Right? So that's a nice example of having the subtraction of vectors come back up. Okay, and in particular here we want A minus B would get us the vector that points from the end of B to the end of A, from the end of the negative vector to the end of the positive one. Okay, and we'll go ahead and we'll say this is theta. All right, so now it's just a matter of taking all of this stuff and plugging it into the law of cosines definition here. All right, so we have C squared. So what's C? It's going to be A minus B. So we're going to have, and C is a length. It's the length of this side. So we want the length of A minus B squared. And then A, so that's going to be this vector here. And we want the length of it squared. And then B. And then vector A, B, cosine theta. Okay. So the next thing that we need to do before we proceed any further is I do need to bring up something, and that is that we do need the definitions for the vectors. So we're going to say let A be A1, A2, so same thing as from the previous page, and then let B be B1, B2. In that case, if we have A minus B, we can go through and use our subtraction definition for vectors to figure out what that is. Okay, so what does it say? It says, if you recall, when we subtract vectors, we subtract their components. So we're going to get A1 minus B1, comma A2 minus B2 squared. And then this is going to be the length of, right? So we're going to have A1 comma A2 squared, B1 comma B2 squared. And then this we're going to leave as it is. Now, why do that? It's because if you go and look at what we're trying to go through and show, we're trying to show that this piece here ends up equaling the other definition, the set definition 2. So we want to just leave this alone because it's already in the definition. It's already in the thing that we're trying to prove. Okay, so here, if we're going to go through and find the length of this, you take the square root of the component squared. That's our length definition for vectors. So we're going to have A1 minus B1 squared, A2 minus B2 squared. And there's that square there. And then the same thing here, the square root of A1 squared plus A2 squared. And then here, B1 squared plus B2 squared. And then this, we're just going to, I forgot something. Oh, my apologies. There's supposed to be a 2 here. And then we get length A, length B. That was just me transcribing the law of cosines incorrectly. And so at this point, the square and the square roots cancel for all of these, and we can expand A1 minus B1 squared. So we're going to get A1 squared minus 2A1B1 plus B1 squared. And then expand this, we're going to get A2 squared minus 2A2B2 plus B2 squared. And then here we're going to have a1 squared plus a2 squared. And then here b1 squared plus b2 squared. And then again, we're going to continue to just leave this. All right, and now if you look at this, we've got this cancels with this cancels with that, this cancels with this cancels with that, and we have minus 2a1b1 minus 2a2b2 equals negative 2 length a length b cosine theta, and then divide both sides by negative 2, and you get length a length b cos theta equals a1 b1 plus a2 b2. And you can see that these are the two definitions. So here we have definition 1 of the dot product is this, definition 2 of the dot product is this, and so we've shown that definition 1 equals definition 2. Okay, so the next thing that we're going to do now that we've gone through and defined our two definitions, explained, how each one works, proved that the two are equal, is we're going to go through and we're going to look at doing some properties of dot products. So why have this definition? What's the point of the dot product? What does the dot product do? All right, so there are some properties of the dot product. All right, so the first property of the dot product is that dot products can be used to find angles between vectors. Okay, so how does that work? Well, if you start off with definition 1, right, and that is that we have length A, length B, cosine theta equals A dot B, we can go through and solve for cosine theta by dividing length A and length B over. So we get cosine theta equals A dot B divided by the length of A, length of B. And then at that point, now that we've got the right-hand side has all of the stuff that we'd like to be able to calculate, we can go through and use definition 2 of the dot product in the numerator here to rewrite this as cosine theta is a1 b1 plus a2 b2 over length A, length B. And now everything on the right-hand side we can calculate. And so we can go through and find cosine theta equals a number. And then you can use the inverse trig function on a calculator to calculate the angle. Okay, so let's go through and try doing some examples. So the first example, let's let A be 1, 3. Let's say B is 3, 2, and we'd like to go through and find the angle between them. Okay, so to do that, we're going to say cosine theta equals A dot B over length of A, length of B. All right, so what would that be? Well, A dot B is going to be the dot product of these, so it's going to be 1 times 3 plus 3 times 2, so we're going to get 3 plus 6. And then the length of A is going to be the square root of 1 squared plus 3 squared, so that's going to be 10. And then the length of B is going to be 3 squared plus 2 squared, so it's going to be 13. And so we're going to get 9 over root 10, root 13. And then if you go ahead and calculate this using a calculator, and then you use inverse trig on your calculator, make sure your calculator is in degree mode, not radian mode. We're going to go through and just find angles with degrees. Then you should get that the angle is roughly, and you should verify this if you have a calculator, is roughly 37.9 degrees. And so we can go through and use the dot product to find the angle between these two given vectors. So that's kind of cool. Let's do a second example. So again, dot products, all these definitions, they all extend to 3 dimensions. So let's see if we can go through and use this in 3 dimensions. So let A be -2, 1, 5, and let B equal 4, 0, -1. And then we can go through and use our definition again. So cosine theta equals A dot B divided by the length of A, length of B. So that's going to equal, so A dot B, we just want to go ahead and multiply and then add the next product and then add the next product. All right, so we're going to have -8 plus 0 plus -5. Oops. That's going to be -13. And then for the length of A, that's going to be the square root. And then you want to just take the components and square them and add. So we're going to have 4 plus 1 plus 25. That's going to be the square root of 30. And then 16 plus 1, that's going to be the square root of 17. And so we get cosine theta equals this. And go ahead and again, calculate this, put it into your calculator, and then it should give you approximately 125.1 degrees. Okay, and so that's the first property of the dot product, is that dot products can be used to go through and find angles between vectors. Property 2. So property 2 relates to orthogonality, and it says that A dot B equals 0 if and only if A and B are orthogonal. All right, so this is the property itself. We'll talk about in a second what it's used for. One thing before we get into that is this new word that you might not be familiar with, orthogonal. It means the same thing as perpendicular. It just means that there's 90-degree angle between the two objects. It's like a 3-dimensional perpendicular. Okay, so this property, which is going to be arguably the most important property from this section, is it's used as a test for orthogonality. So it's used as a test to determine whether two vectors are orthogonal. Two vectors are perpendicular. And then it's also used in theories and proofs. Okay, so what we want to go through and do with it is we want to prove that this is true. Okay. This is a very good example of a simple proof. It's easy to understand, and you want to get started with proofs that are easy to understand. And so first thing we're going to look at is this. Well, maybe I should have mentioned earlier that if you're not familiar with this, what does that mean? This IFF. It means that the implication goes both ways. It means that this statement here could be written as if this, then this, or if this, then that. That both are true. Okay, so this could be written if A dot B equals 0, then A and B are orthogonal. or it could be written the other way, which I'll actually write down in a second. So when you see the IFF like that, so it means that the implication goes both ways. It's also referred to as equivalency. So it means that this is equivalent to this. Okay, so equivalency is not, if you just have just an if-then statement does not imply equivalency, that the order does matter in an if-then statement. So if I just wrote this does not mean the same thing as this. So the order here matters. You have to have this. This implies this, but this does not imply that if you don't write them both, if you don't write it both ways. Okay, so there is this is a stronger statement with the IFF. It means that these two are equivalent statements, or that the implication goes both ways. Okay, so let's go through and do the proof. And to do the proof, you have to prove this both ways. So the first way we're gonna do is that if this, then this. All right, so the way that you go through and do an if-then proof, you want to start with supposing that this is true, and then see if you can go through and work your way to the other statement. All right, so you can say let A dot B equals 0. Okay, assuming that is true, we can go through and use that first definition for the dot product. This is the same thing as A, B cosine theta equals 0. Okay, and now this statement here, if you have this statement and you know that A and B are non-zero vectors, okay, so if this theorem here would be true, non-trivially true, if these are for non-zero vectors. If the vectors are 0, then of course the dot product is going to be 0. And if a vector is 0, then if one vector is 0, can you even have orthogonality between two vectors? It doesn't even really make sense. So it's kind of implied that we're talking about vectors that are non-zero vectors. And if they're non-zero vectors, that means that the length of a non-zero vector is just going to be a number, and here the length here is going to be a number. And so, long story short, we can go through and we can divide these over to the other side, and they just go away. Okay, so we're going to get cosine theta equals 0. And if you have cosine theta equals 0, then what does that tell you about theta? It tells you theta is 90 degrees, assuming that we are restricted. And we're not talking about all possible thetas. We're talking about in a triangle sense. We're talking about between 0 and 90. So once we have theta is 90 degrees, then that tells us that the angle, so this is the angle between the two vectors is 90 degrees. So thus A and B are orthogonal. Right, because that's what we defined orthogonality to be. It means that the two vectors are perpendicular, which means that the angle between them is 90 degrees. So that completes the proof. Okay, so we started off with let A dot B equals 0. Then we were able to go to here, then here, and that implied this, and then that gets us to the A and B are orthogonal. Okay, so that proves the vector in one direction. It proves that if we have A dot B equals 0, then A and B are orthogonal. However, to complete the proof has to go both ways. Okay, so maybe I don't know if we're gonna have enough space, but let's go through, because I like to keep this on the same page because it's kind of neat to see the two sides. So to go through and prove the other side, we have is we're going to say if A and B are orthogonal, I don't know what happened there at the end, it turned into a D. Then A dot B equals 0. Okay, so we can start off with let A and B be orthogonal. Okay, if A and B are orthogonal, then the angle between A and B is 90 degrees. Let's Let's do this. And if theta is 90 degrees, then cosine of theta equals 0, right? Because cosine of 90 degrees is 0. And then if cosine of theta equals 0, then we could multiply on both sides by length of A and length of B, again, assuming that they're non-zero. And then we can go through and use our definition 1 to say that A dot B equals 0. And that completes the proof. And the reason I wanted to keep these on the same page is that if one of the things you'll notice is that if you took this and think about going this way, like direction wise, as far as the proof starting here and working your way down, this proof does exactly the opposite, right? So this arrow, if you wrote it, would look like this. Okay. And so that's not necessarily common, but it does happen. So when it comes time to go through and prove an if and only if, at times the method that you use to go through and prove one direction on the if and only if is you can use to go through and prove the other direction on the if and only if. And I think I just said something that I didn't mention earlier. This is translated into if and only if. Okay. So now what we can do with this is we can use it as a test to go through and prove that two vectors are orthogonal. So if we have, let A be 1 comma -2 and B equal 2 comma 1, and you're asked, are A and B orthogonal? Now, generally, you can't tell that just by looking at the vector. It's not going to just be apparent that if you were to go through and graph these, that the angle between them is 90 degrees. So what we want to be able to do is we want to be able to have a quick and easy test, and that's what we went through and just defined. So are A and B orthogonal? To figure that out, you can go through and calculate what A dot B is. If you do that, you're going to get A dot B equals 2 minus 2 equals 0. Since A dot B equals 0, we can say A and B are orthogonal. Okay, and if you picked a different A and B, so if you have, let's say A was 2 comma 3, B equals -2 comma 3, and you're asked, are these orthogonal? You can go through and check that by calculating A dot B equals 2 times -2, that's -4, plus 9 equals 5. All right, so A dot B equals 5. Since A dot B is not equal to 0, then A and B are not orthogonal. Oops. Okay, and so that's property 2. The dot product gives us a test to go through and check for orthogonality. All right, so for two vectors to be orthogonal, their dot product has to be 0. So if it's not 0, then we know that they're not orthogonal. 3, projections. So we're going to go through and use the dot product to define a new thing called a projection. So let's say we have that original picture. Here's A. Here's B. We go through and we take this A and we drop down a piece that is perpendicular to B. That creates this thing here, which we said was, assuming we've got this is theta, length of A cosine theta. So what we're going to do with this thing here is we're going to create two definitions with it. So definition one, we're going to call the component of A in the B direction, and it's going to equal this value. It's going to equal this thing. So this thing that we've been talking about, the length of this piece here that we've written on the board a couple times, it's important enough that we're actually going to have a definition strictly for that. So we're going to say the component of A onto B is this, okay? And we can go through and take the definition, the first definition for dot products, and we can write this in a simpler, more palatable form, right? So if we recall that A dot B equals length A, length B, cosine theta, then if you divide the B over, we're going to get the A dot B over the length of B equals length of A cosine theta. And so this component here equals, we can replace this with the left-hand side here, and so it equals A dot B over the length of B. So that's one of our definitions, is this piece. Comes up often enough, it's important enough that we want to go through and have a definition for it. And this is our definition. We're going to call it the comp of A onto B. This is comp is short for component, and it equals A dot B over the length of B. The second definition, which I'll get into more in a moment, is going to be called the projection of A onto B. And I'm just going to give you the formula for that, and we'll go through and verify it in a second. Okay, so what that is, let me change colors here, is it's this vector here. So it's in a sense, it's the vector version of this. It's the vector form of the component. Okay, and it has this as its formula. Okay, so before I go through and maybe explain this further, now that we have these two formulas, let's go through and make sure that we can use them to calculate some projections, right? Let me actually comment one moment more before we do that, and that is that, so what does this have to do with projection, the word projection? What's the relationship there? Okay, well, the idea here is that if you think about it in terms of a film projection, right? So if you put your hand in front of a light that's being cast, right? It casts a shadow, right? It casts a shadow onto a screen. So if you think about it as there's a light up here, like I draw like a little sun. If there were a sun shining up here that was perpendicular to B, then the shadow that would be cast from A onto B would be this red vector. Okay, so the shadow that you would end up getting, so it's going to be the projection, just like you would with a shadow, when it comes to putting your hand in front of a movie projection. It's the same idea. So that's at least that's the way that I think of the definition of the projection, is that it's a shadow. So it's the shadow that's cast from A onto B. And we have two pieces to it. One is the length of the shadow. That's the component of A onto B. And then the other one is the vector shadow. And that's the projection of A onto B. There are other versions, other ways of thinking of projections. So sometimes, again, they think of it in terms of components. So you think of it's the component of A that lies on B. So if you took A and you split it into two pieces, right? If you recall when we went through and defined vectors in a previous section, we went through and said that if you have the vector and you went through and were to sketch it, right? And you cut it into pieces, right? We had this was A1 and this was A2 for vector A. So you could think about this as you have the components of A are A1 and A2. You've got two pieces to form A. So it's part A1 and it's part A2. If you apply the same idea here, then you could think of this piece as the component of A that's in the B direction. It's the component of A that aligns with B. And so that's where you get into comp, and that's where you get into component talk when it comes to projections, is that the shadow here also is the piece of A that it aligns with B. So anyway, that's the idea behind projections, and maybe helps to fill in the definition and have it make more sense. Okay, so let's go through and use these two definitions to actually calculate some projections. So let's say A is -1, 3. B is 2, 1. And then we can go through and find the projection of A onto B. Okay, so if you recall the formula from the previous page, that's A dot B over the length of B squared times B. All right, so to go through and calculate that, we want to calculate the dot product and put that in the numerator. So the dot product, you multiply, and then add. So we're going to get -2 and 3, and then add. -2 plus 3 is 1. And then we have the length of B squared. So that's going to be the square root of, we want to square the components and add them. So 2 squared is 4, 1 squared is 1, 4 plus 1 is 5. So we're going to get the square root of 5 squared. And then B here, to finish the calculation, you just want to write B. So it's going to be times 2, 1. So this is going to be a scalar times B. And the scalar that we're going to get is going to be 1/5 times 2, 1 equals 2/5, 1/5. All right, so this would be the projection. This is the part of A here that aligns with B. Okay, and you could, if you wanted to, draw yourself a little picture to kind of, verify this. And if you do a good job with your picture, you should be able to end up getting a result that looks like this. All right, so what do we have? So -1, 3. So we could say this is -1. I don't know, maybe there's -1, 3. It's only going to work if you do a good job of this. And then let's say we've got 2, 1. So 1, 2, 1. And then if you go through and drop down a line that's perpendicular, it's going to look something like that. And so you can see this little tiny vector that we ended up getting, which I can try and color in red here for you. The head basically fills the whole thing. That little tiny vector there, if you were to go through and try and identify what its components would be, it would be 2/5 in the x direction and 1/5 in the y direction. That looks about right. Well, I don't know, maybe not. If you look at, if this is supposed to be 1, then this distance here is, that's about right, actually. 2/5 is about 0.4. That's pretty close. So I did a pretty good job. Okay. Anyway, so that's how you calculate the projection, and then all of this stuff, just to stick with the point here, it can be extended to 3 dimensions, and so let's go through and calculate 3 dimensions. Let's say A equals 1, 2, 3, and B equals -2, 1, 4. And then we can calculate the component of A onto B. So this is going to be the length of the projection, or the length of that shadow that's cast. And that's A dot B over the length of B. And so A dot B, we're going to get -2 plus 2 plus 12. All right, so -2 plus 2 is 0, plus 12 is going to be 12. And then the length of B is going to be the square root of 4 plus 1 plus 16. 4 plus 1 plus 16, that is 21. Okay, and so this is going to be the length of the shadow. All right. So the next thing I went through and did is to spend a minute talking about trying to connect the two projection formulas. So this is an interesting tool that you need to have, right? So connecting the projection formulas. Okay, so how can you do that? All right, so let's kind of go back to the definition. We have vector A, vector B. We can go through and drop down a 90-degree angle here. And then we know that this distance from here to here is the length of A cosine theta. And then we also want to be able to go through and define this vector here. All right, so how do we go through and, knowing that this is the length of A cosine theta, how do we go through and use that to create a vector? So let's spend a second talking about that. All right, so first of all, just this is also the component. Oops, still using red there. So as we've said, this is also, we call this the component of A to B. And we also know that the component of A onto B, as we proved earlier, is A dot B over the length of B. It has a nice simple formula. Okay, so how do we go through and take that and use that to find this vector? Well, what we need to do is we really need to take kind of two pieces and put them together. So what do we know about this red vector? Let's call this red vector vector V. We know that vector V has length A dot B over the length of B, and we know that V points in the direction of B. Okay, so it's got two qualities, vector V there, the red vector. All right, so the fact that V points in the same direction as B is going to be the key to this. So what we can do is we can go through and take vector B and we can turn it into just a length by going through and making it into a unit vector by normalizing it. So you can go through and you can normalize B. If you do that, then you end up with B over the length of B. Now this has length 1. All right, so if you went through and calculate the length of this, it would be 1. Now, what if we wanted to have a vector that pointed in the same direction as B, but had length 2, right? So what if we wanted a vector, not this vector, because this vector has length 1. What if we wanted a vector that had length 2? Well, if this has length 1, to go through and find a vector that's twice as long as that, think back to our scalar multiplication definition. We could just take this vector and multiply it by 2. So if we wanted a vector that had the same direction as this, if we wanted a length 2 version of this, we would go through and just multiply by 2. Okay. Now, that's of course not what v is. What is v? V points in the same direction as b, so it's in the same direction as this unit vector, but it's not length 2, it's length this. Okay, so to go through and calculate what v is, right, which is what we've been calling the projection of a onto b, what we need to do is take this definition here, which is the length that we want, and multiply by this definition, which is the direction. So this is a useful tool that you really need to have in your toolkit, and that is how do you construct vectors that have a length that you want and a direction that you want. You have two separate pieces, and what you do is you want to take the direction, turn it into a unit vector, and then multiply by the length. And if you do that, we get a dot b over the length of b times b over the length of b. And then if you simplify that, this here can be combined with that, and we'll end up with a dot b over the length of b squared times b. Okay, and that gives us our projection definition. So that's where the projection definition comes from. It's a matter of taking the component definition and then multiplying by the unit vector to give it a direction. Okay, so that is property 3. And there's more. All right, there's one more property, property 4. Work. Okay, so one of the things that we need to do if we're going to talk about work is to recall, right, from a physics class, if a force F is applied over distance d, then work is defined to be force times distance. Okay, so there's our definition for work. It's just force times distance. Now, the key to this definition, and if this is going to matter in terms of what we're going to talk about today, is that F and D are in the same direction. Okay, so that's all recalled from a previous physics course. Okay, so now what we're going to look at in terms of dot products is we're going to say let F and D not be in the same direction. So let's say we've got vector F that represents a force and vector D, which represents movement, and they are not in the same direction. So in that case, be given by the following picture. So we've got here's F, and it's applied off at an angle like this, and then here's D. This is the distance over which it's applied, right? And we've got angle theta. Okay, so in order to go through and calculate work, what we need is we need the two of these to align. So let's just go through and say, to calculate the work, F and D need to be in the same direction. So how do we go through and get them to be in the same direction? Because right now they're not, right? F, it's if you think about D as being flat here, it would be like you're pushing an object and you're pushing upward at an angle on the object instead of pushing in the same plane as D. So in order to go through and get F and D to be in the same direction, what we can do is we can use all of the information that we've been applying today, and that is we can go through and say, let's take the part of F that points in the same direction as D. Okay, and so that would be find 90-degree angle. So that is going to be the length of F cosine theta is going to be this distance here. All right, so this, by going through and finding this, we'd be taking F and aligning it with D. So now we're finding the part of F that points in the same direction as D. Okay, so if we go through and do that, this is now going to be aligning with D, and we could go through and calculate our work using those quantities. So we start off work is, we know it's force times distance, and then the force, the part of the force here that aligns with D, because they have to be in alignment, they have to be in the same direction, is not going to be this big F here. It's going to be this portion of it, F cosine theta. And then D is how far we're going to move it. So that's going to be the full distance of length of D here. That's going to be that quantity. And if you put those together, you get length F, length D, cosine theta. And so this says that the work is equal to the dot product. So if you have two vectors, one vector that's the force and one vector that's the distance that you're, moving an object over that the force is applied to, then the work is it's as simple as just taking the dot product of the two. Okay, so let's just look at a quick example. If a force F is applied in direction 1, 2 on an object that is moved a distance (4, 0), how much work is done? So this is the example that literally we just said. So 1, 2, that means that you're pushing you're pushing upward. You have this upward, that's the 2 here that's on this. Some of your force is being applied upward, and that upward part of the force is useless for moving the object in the direction and a distance 4, 0. And so when it comes time to go through and calculate the force, we're not going to take the length of this and multiply by the length of this. Instead, work is going to equal the dot product of the two. So we want 1, 2 dot 4, 0. And then that ends up equaling 1 times 4 is 4 plus 2 times 0 is 0. And we end up getting 4. Okay. So that is our fourth and final property of dot products is work. Okay, so that concludes this video on the dot product. Thank you for watching. I'll see you next time.